Hello everyone, I am MD Atif Hussain and today we are going to discuss on the topic history of ancient mathematics. Let us first go briefly into history of mathematics till today's date and then we will dig into a particular topic today, that is history of ancient mathematics. When did mathematics begin? Naive questions like this have their place in history. The answer is usually a counter question. In this case, what do you mean by mathematics? The history of mathematics is nearly as old as humanity itself. Since antiquity, mathematics has been fundamental to advances in science, engineering, and philosophy. It has evolved from simple counting, measurement, and calculation, and the systematic study of the shapes and motions of physical objects to the application of abstraction, imagination, and logic to the broad, complex, and often abstract discipline we know today. From the notched bones of early to the mathematical advances brought about by the settled agriculture in Mesopotamia and Egypt, and the revolutionary developments of ancient Greece and its Hellenistic empire, the story of mathematics is a long and impressive one. The East carried on the baton, particularly China, India, and the medieval Islamic empire, before the focus of mathematical innovation moved back to Europe in the late Middle Ages and Renaissance. Then a whole new series of revolutionary developments occurred in 17th century and 18th century. Europe setting the stage for increasing complexity and abstraction of 19th century mathematics, and finally the audacious and sometimes devastating discoveries of the 20th century. However, in this presentation, we are concerned only about the history of ancient mathematics. So let us begin it now. Let us first start with the prehistoric mathematics. Our prehistoric ancestors would have had a general sensibility about amounts and would have instinctively known the difference between, say, one and two antelopes. Now let us look into the picture. We have the Isango bone, a tally stick from Central Africa dated from about 20,000 years ago. That's really a long time. Here the tally sticks means counting sticks. They must have had the abstract idea of counting by sticks and all. But the intellectual leap from the concrete idea of two things to the invention of a symbol or word for abstract idea of two took many ages to come about. Even today, there are isolated hunter-gatherers in the tribes in Amazonia which only have words for one, two, and many, and others which only have words for numbers up to five. In the absence of settled agriculture and trade, there is a little need for formal system of numbers. Early man kept track of regular occurrences such as phases of moon and seasons. Pre-dynastic Egyptians and Sumerians represented geometric designs on their artifacts as early as the 5th millennium BC, as did some megalithic societies in northern Europe in the 3rd millennium BC or before. But this is more art and decoration than the systematic treatment of figures, patterns, forms, and quantities that has come to be considered as mathematics. Now, let us see the history of mathematics in Sumeria and Babylonia. Okay, let us do it now. Sumer, a region of Mesopotamia, modern day Iraq, was the birthplace of writing, the wheel, agriculture, the ark, the plow, irrigation, and many other innovations, and is often referred to as cradle of civilization. The Sumerians developed the earliest known writing system, a pictographic writing system known as a cuneiform script. Now, what do you mean by cuneiform script? It means using a wedge-shaped character inscribed on blocked clay tablets. Now, what does this imply? This implies that they had this written and imprinted form of knowledge of mathematics, and this has meant that we actually have more knowledge of the ancient Sumerian and Babylonian mathematics than of the early Egyptian mathematics. Indeed, we even have what have appeared to school exercises in arithmetic and geometric problems. Here in the picture we have Sumerian clay stones, and we can see the cuneiform script about which I was talking in the last slide. As in Egypt, Sumerian mathematics initially developed largely as a response to bureaucratic needs when their civilization settled and developed agriculture, possibly as early as the 6th millennium BC, for the measurement of plot of land, the taxation of individuals, etc. In addition, the Sumerians and Babylonians needed to describe quite large numbers as they attempted to chart the course of the night sky and develop their sophisticated lunar calendar. They were perhaps the first people to assign symbols to group of objects in an attempt to make the description of large numbers easier. They moved from using separate tokens or symbols to represent sheaves of wheat, jars of oil, etc., to the more abstract use of symbol for a specific number of anything. Starting as early as the 4th millennium BC, they began using a small clay cone to represent 1, a clay ball for 10, and a large cone for 60. Often, the course of the 3rd millennium, these objects were replaced by cuneiform equivalents so that the number could be written with the same stylus that was being used for words in the text. A rudimentary model of the abacus was probably in use in Sumeria from as early as 2700 to 2300 BCE. Now let us look at the Sumerian and Babylonian number system, which has the base 60. In today's time, we normally use decimal number system with base 10. We often see binary number system with base 2 for purposes such as understanding machine language. Sometimes we also study octal system with base 8 or hexadecimal system with base 16. However, let us not go deeper into that, and let us see the Sumerian and Babylonian number system which had the base 60. Sumerian numeric system, which was a sexagesimal or base 60 numeric system, which could be counted physically using the 12 knuckles on one hand and the 5 fingers on the other hand. So 12 into 5 makes it 60. Unlike those of the Egyptians, Greeks, and Romans, Babylonian numbers used a true place value system where digits were written in the left column represented larger values, much as in the modern decimal system, although of course using base 60 and not base 10. Thus, this part in the Babylonian system represented 3661. Now, in decimal system, how do we represent 3661? We do it by like 3 into 10 power 3 plus 6 into 10 power 2 plus 6 into 10 plus 1. But in Babylonian system, how do we do that? We do that in the way like this. See it here. 60 to the power 2 plus 60 plus 1, which makes this number 3661. Also, to represent the numbers 1 to 59 within each place value, two distinct symbols were used. A unit symbol, this was a unit symbol, and a tens symbol, this was the tens symbol, which were combined in a similar way to the familiar system of Roman numerals. We already know that. For example, let's see how 23 was written. This was 1113, and this is 2, so 23. Now how do we write 83? So this is 60 and this is 23, so 60 plus 23 is 83. But one thing you might have noticed, that for representing 1 and for representing 60, they were using the same thing, so it created confusion. Thus, the actual place value of symbol often had to be inferred from the context which we are using. Here in the figure we have the Babylonian number system, and here you can see 1 to 60, the complete thing about which we were talking on the last slide. It has been conjectured that the Babylonian advances in mathematics were probably facilitated by the fact that 60 has many divisors: 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30 and 60. In fact, 60 is the smallest integer divisible by all integers from 1 to 6, and the continued modern day uses of 60 seconds in a minute, 60 minutes in an hour, and 360, which is 60 into 6 degrees in a circle, are all testaments to the ancient Babylonian system. It is for the similar reason that 12, which has a factor of 1, 2, 3, 4 and 6, has been such a popular multiple historically. For example, 12 months, 12 inches, 12 pins, 24 hours, that is 2 into 12, 24 hours. The Babylonians also developed another revolutionary mathematical concept, something else that the Egyptians, Greeks and Romans did not have: a circle character for 0. Although its symbol was really still more of a placeholder than a number in its own right. Now let us study about the Babylonian clay tablets. We have evidence of the development of a complex system of metrology in Sumer from about 3000 BC, and multiplication and reciprocal division tables, tables of squares, square roots, cube roots, geometrical exercises and division problems from around 2600 BC onwards. Later Babylonian tablets dating from about 1800 to 1600 BC covered topics as varied as fractions, algebra, method for solving linear, quadratic and even some cubic equations, and the calculation of regular reciprocal pairs. But the way of Babylonian reciprocal system was not as we have today. How do we find reciprocal in today's time? For example, let us take the number 8. What will be its reciprocal? Its reciprocal is 1 upon 8. But how do we get that? We see that 8 into something gives 1. And what is that something? It is similar as 8x equal to 1, so x equal to 1 upon 8. However, the pairs of numbers which multiply to give 60, this was the reciprocal pairs in the Babylonian times. One Babylonian tablets gives an approximation to root 2 accurate to astonishing 5 decimal places. This were somehow representing that they were also aware of the concept of linear equations and all. Other lists the square of numbers up to 59, the cubes of number up to 32, as well as tables of compound interest. Yet another give an estimate for pi of 3 whole 1 to the power 8, that is 3.125. A reasonable approximation of the real value of pi, which is 3.1416 and so on. The idea of square of numbers and quadratic equations, where the unknown quantity is multiplied by itself, for example x square, naturally arose in the context of measurement of land, and Babylonian mathematical tablet give us the first ever evidence of the solution of quadratic equations. The Babylonian approach to solving them usually revolved around a kind of geometric game of slicing up and rearranging shapes. Also, although the use of algebra and quadratic equation also appears. At least some of the examples we have appear to indicate problem solving for its own sake rather than in order to resolve a concrete practical problem. This meant that they had started doing pure mathematics also rather than just applied mathematics or the applying mathematics in practical fields. The Babylonians used geometric shapes in their buildings and designs and in dice for the laser games which were so popular in their society, such as the ancient game of Backgammon. Well, I don't know much about that game, the rules of that game, but might be of something with the tablets. Here we have the Babylonian clay tablets from 2100 BC, showing a problem concerning the area of irregular shape. Their geometry extended to the calculation of areas of rectangles, triangles, and trapezoids, as well as volume of simple shapes such as bricks and cylinders, although not pyramids. Well, about the pyramids, we will see in the Egyptian mathematics. The Plimpton 322 clay tablet. The famous and controversial Plimpton 322 clay tablet, believed to date from around 1800 BC, suggests that the Babylonians may well have known the secret of right angle triangles, that the square of hypotenuse equal to the sum of squares of the other two sides, many centuries before the Greek Pythagoras theorem. The tablet appears to list 15 perfect Pythagorean triangles with whole number sides, although some claim that they were merely academic exercises and not deliberate manifestation of Pythagoras triplets, which means that they might not have the proof, or or they might don't want to prove it, or they might have only few examples, but maybe it was possible that they were knowing Pythagoras theorem, but that is just an assumption, so we will not consider that. Now let us look at the Egyptian mathematics, which involved the numbers and numerals. The early Egyptians settled across the fertile Nile Valley as early as about 6000 BC, and they began to regard the pattern of lunar phases and the seasons both for agricultural and religious reasons. The pharaoh's surveyors used measurements based on body parts. A palm was the width of the hand, a cubit measurement from elbow to fingertips, to measure land and buildings very early in Egyptian history, and a decimal numeric system was developed based on our 10 fingers. The oldest mathematical text from ancient Egypt discovered so far, though, is the Moscow Papyrus, which dates from the Egyptian Middle Kingdom around 2000 to 1800 BC. Now let us see the ancient Egyptian number system. It is thought that the Egyptians introduced the earliest fully developed base 10 numeration system at least as early as 2700 BC, and probably much early, yes. Written numbers used a stroke for units, a heel bone symbol for tens. In the figure you can also see all the symbols. A coil of rope for hundreds, a lotus plant for thousands, as well as other holographic symbols for higher powers of 10 up to a million. However, there was no concept of place value, so larger numbers were rather unwieldy, although um, what do you mean by unwieldy? So here we have like for example, the million required just one characters. Here you can say they are representing millions by just one character, but a million minus one required 54 characters. So it was a bit complicated, really. The Rhind papyrus, dating from around 1650 BC, is a kind of instruction manual in arithmetic and geometry, and it gives us explicit demonstration of how multiplication and division was carried out at that time. It also contains evidence of other mathematical knowledge, including unit fraction, composite and prime numbers, arithmetic, geometric and harmonic means, and how to solve first order linear equations, as well as arithmetic and geometric series. The Berlin Papyrus, which dates from around 1300 BC, shows that ancient Egyptians could solve second order algebraic or quadratic equations. Now, multiplication. Now, let us see how they do that. Multiplication, for example, was achieved by a process of repeated doubling of the number to be multiplied on one side and one on the other, essentially a kind of multiplication of binary factors similar used by modern computers. Now let us see the figure and try to understand what I have just said. This was a sophisticated system. Now let us see how they do 3 into 6. Multiply 3 by 6. Let us represent 3 red dots by 1. Then for 6 red dots we have 2 black dots. Now 6 equal to 2 plus 4. So for here 2, and we are left with 4 more black dots. These are 4 more black dots, and for 4 black dots now we will have 6 red dots. So adding them, now we will add them. So what do we get? 18, and that is actually the multiplication of 3 into 6. Well, you might not be able to what I understand clearly what I want to say, but if we try it for other multiplication as well, just such as for 4 into 24 and other things, we will surely find that this process yield correct result. These corresponding blocks of counters could then be used as a kind of multiplication reference tables. First, the combination of powers of 2 which add to the number to be multiplied by was isolated, and then the corresponding blocks of counters on the other side yielded the answer. This effectively made use of concept of binary numbers over 3000 years before Leibniz introduced it into the West, and many more years before the developments of computer was to fully explore its potential. Practical problems of trade and the market led to the development of a notation for fractions. The papyri, which have come down to us to demonstrate the use of unit fraction based on the symbol of I of Horus, where each part of the I represented a different fraction, each half of the previous one, that is half, quarter, eighth, 16th, 32nd, 64th, and so on. So the total was 1/64th sort of a whole, the first known example of a geometric series. Here you can see that it is geometric series. Unit fractions could also be used for simple division subs. For example, if they needed to divide 3 loaves among 5 peoples. Here in the figure we also have the same things. Now how they do that? First, they divide the 2 loaves into 3 parts each. 3 parts each, and the third loaf into 5 parts. And from these 2 loaves, we take out one part and divide that part into 5 parts. Now how much each person get? each person will get 1 upon third plus 1 upon 15 this part plus 1 upon 5 this part. So the total comes out to be 3 upon 5, which we would have expected. The Egyptians approximated the area of circle by using shapes whose area they did know. They observed that the area of circle of diameter 9 units, for example, was very close to the area of square with side 8 units, so that the area of circle of other diameters could be obtained by multiplying the diameter by 8 upon 9 and then squaring it. This gives an effective approximation of pi accurate to within less than 1%. The pyramids themselves are another indication of the sophistication of Egyptian mathematics. Setting aside claims for that the pyramids are first known structures to observe the golden ratio of 1:1.618, which may have occurred for purely aesthetic and not mathematical reasons. There is certainly evidence that they knew the formula for volume of pyramid, that is 1 by third times the height times the length times the width, as well as that of a truncated or clipped pyramid. They were also aware long before Pythagoras of the rule that a triangle with sides 3, 4 and 5 yields a perfect right angle triangle. In fact, the 3, 4, 5 right angle triangle is often called the Egyptian. The Egyptian builders used ropes knotted at intervals of 3, 4 and 5 units in order to ensure exact right angle triangles for their stonework. We have discussed about the number system, arithmetic, algebra and geometry in ancient Egypt and Mesopotamia, that is the Babylonian number system. Now let us look after some other number system, arithmetic and geometry. Khufu, an Inca counting system. This was the ancient South American civilization of the Inca Empire, a highly developed civilization able to track all important facts required to rule such a vast empire. They did this using a memory tool made of knotted string called a khufu. Since they had no written language and very few ancient khufu are left, we can only speculate what the khufu was actually used for. It's fortunate khufu are still used today, so we may be able to learn about the ancient ones by seeing how the modern ones are used. Combine this with oral traditions, and it appears they were used to keep records on the number of things. Another mystery which remains is what base did the Inca use? All their neighbor used a base 60, but it appears that the Inca used base 10. Recent discoveries as yet unsubstantiated back this theory. Now see the Mayan number system. The Mayan system used a combination of two symbols. A dot was used to represent the units 1 through 4 and a dash was used to represent 5. The Mayan wrote their numbers vertically as opposed to the horizontally, with the lowest denomination on the bottom. Let us see and try to understand it through the figures. For 0, they represented 0 in this form. This is 1, 2, 3, 4, 5. 5 plus 1, 6, 5 plus 2, 7, and so on till 19. Actually, they were using the base 20. For 20, they used to write this is 20 plus 0, that is 20. 20 plus 1, 21. 20 plus 2, 22. 20 plus 3, 23, and so on, 25. Now what does this mean? This means 2 times 20 plus 0, that is 40. What does this mean? 5 times 20 plus 0, that is 100. This is 5 times 20 plus 1, 101. The system was set up so that the first 5 place values were based on the multiples of 20. I have already said that the base was 20. Now let us see the history of Hindu and Arabic numeral system. The Hindu-Arabic numeral system is a decimal place value numeral system that uses a zero glyph as in 205. Its glyphs are descended from the ancient Brahmi numerals. The full system emerged by the 8th to 9th centuries and is first described outside India in Al-Khwarizmi's on the calculation with Hindu numerals. And second, Al-Kindi's 4-volume work on the use of Indian numerals. Today, the name Hindu-Arabic numeral is usually used. Let us see the decimal system. The historians trace modern numerals in most languages to the Brahmi numerals, which were in use around the middle of the 3rd century BC. The place value system, however, developed later. The Brahmi numerals have been found in inscriptions in caves and on coins in regions near Pune, Maharashtra, and Uttar Pradesh in India. These numerals, with slight variation, were in use up to 4th century. Let us see its development in India. During the Vedic period 1500 to 500 BC, motivated by the geometric construction of the fire altars and astronomy, the use of numerical system and of basic mathematical operations developed in northern India. Hindu cosmology required the mastery of very large number such as the Kalpa, the lifetime of universe, said to be 4,320,000,000 and other such things. The form of numerals in Ashoka's inscription is the Brahmi script, which involved separate signs for the numbers 1 to 9, 10 to 90, 100 to 1000. A multiple of 100 or 1000 was represented by a modification of the sign for the number using the sign for multiplier number. Here we can see the Bhakshali manuscript, detail of the dot 0. This is dot represented 0. Here we have the first Brahmi numerals, which was the ancestor of Hindu Arabic numeral system. It was used by Ashoka in his edicts Edicts of Ashoka. In his sextimal text of 499 CE, Aryabhat devised a novel positional number system using Sanskrit consonants for small numbers and vowels for powers of 10. A more elegant Katapaidism was devised in later centuries representing a place value system including 0. Now let us see its adoption by the Arabs. Although we are moving to the medieval times from the ancient times, which is not the scope of our topic, but it is important to mention how the Hindu Arabic system was actually adopted by the Arabs. So I am mentioning that. Before the rise of the Caliphate, the Hindu Arabic numeral system was already moving west and was mentioned in Syria in 662 AD by the Nestorian scholar Severus Sebokht, who wrote the following: I will omit all discussions of the science of the Indians, of their subtle discoveries in astronomy, discoveries that are more ingenious than those of the Greeks and the Babylonians, and of their valuable method of calculation, which surpass description. I wish only to say that this computation is done by means of 9 signs. If those who believe because they speak Greek that they have arrived at the limit of science would read the Indian text, they would be convinced, even a little late in the day, that they are the others who know something of value. In his text, The Arithmetic of Al-Uqaydisi, E.S. Sidon's studies were unable to answer in full how the numerals reached the Arab world. It seems plausible that a direct drifted gradually, probably before the 7th century, though two channels, one starting from Sindh, undergoing Persian filtration and spreading in what is known as the Middle East, and the other starting from the coast of the Indian Ocean and extending to the southern coast of the Mediterranean. So it was not much clear that how the system traveled to the Arabian part. Now let us look at the impact of Hindu-Arabic system on arithmetic. The significance of the development of the positional number system is described by the French mathematician Pierre-Simon Laplace wrote, "It is India that gives us the ingenious method of expressing all numbers by the means of 10 symbols, each symbol receiving a value of position as well as an absolute value, a profound and important idea which appears so simple to us now that we ignore its true merit, but its very simplicity and great ease which it has lent to all computation puts our arithmetic in the first rank of useful innovations, and we shall appreciate the grandeur of this achievement when we remember that it escaped the genius of Archimedes and Apollonius, two of the greatest minds produced by the antiquity. So this much was the importance of our Hindu-Arabic numeral system. Now let us see the history of negative numbers. Let me first make it clear that I tried to find out the history of negative numbers in ancient times in internet and textbooks, but I did not find much of its evidence in ancient times. So we are looking just brief history of negative numbers and also how it developed in medieval times. 570 to 500 BC Greece. The Pythagoreans thought of a number as a multitude of units. Thus, one was not a number for them. There was no indications of negative numbers in their work. 4th century BC Greece. Aristotle made the distinction between number, that is natural numbers, and magnitude, which is divisible into divisibles that are infinitely divisible, but give no indication of the concept of negative numbers or magnitude. 300 BC Greece. Books 7, 8 and 9 of Euclid's Elements concern the elementary theory of numbers. Euclid continues Aristotle's distinction between number and magnitude, but there is still no indication of negative numbers. 100 BC to 50 CE China. The 9 chapters on the mathematical art. Negative numbers were used in the chapter on solving system of simultaneous equations. Red dots were used to denote positive coefficients, black to denote negative ones. Rules for signed numbers were also given. 3rd century CE Greece. The first indication of negative numbers in the Western world was in the Diophantus Arithmetica, in which he referred to the equation which in modern notation would be represented as 4x plus 20 equal to 0 as absurd, since it would give the solution x equal to minus 4. He also said a number to be subtracted multiplied by a number to be subtracted gives a number to be added. That is, minus into minus gives plus. So for example, he could deal with the expressions such as 9 in modern notations, x minus 1 times x minus 2. However, Diophantus gave indication that he had no conception of abstract notation of negative numbers. Seventh century CE India. Negative numbers were used to represent debts when positive numbers represented assets. Indian mathematician or astronomer Brahmagupta used negative numbers to unify Diophantus' treatment of quadratic equation. from three cases: ax square plus bx equal to c, bx plus c equal to ax square, and ax square plus c equal to bx, to the single case which we are familiar with today. He gave rules for operation with negative numbers. 9th century CE Middle List. Although the Arabs were familiar with negative numbers from the work of Indian mathematicians, they rejected them. Muhammad ibn Musa al-Khwarizmi's textbooks Al-Zabr wal-Muqabla, from which he got the word algebra, did not use negative numbers or negative coefficients. Thus, his discussion of quadratic equation dealt with 6 different types of equations rather than one general form we use. Well, we will not go further into that because we have already come to the medieval times. So let us wrap up. Over the times, mathematics grew, and in the medieval and modern period, but the efforts of ancient mathematicians can never be neglected. Because of their efforts, the mathematics originated and keep evolving over time. Finally, we are at a stage where we can do rigorous pure mathematics and apply mathematics in various aspects of life. Hence, once again, we should thank them. These are my references. You can see it. That's all from my side. Thank you and thanks for listening. Have a wonderful day. Right?